Thanks for the invitation, and it's my pleasure, in fact, to talk about this. And also, our new complex system group has just taken birth a few months back in IIT Kanpur, and we look forward to strong interactions within the department, outside department, and this is one. I mean, it was an opportune moment that immediately after a group was formed, this Nobel Prize came in this field. Okay, so this is the title: Global Warming, Butterfly Effect, Climate Change, and this is my website if you need some more details. Okay, so these are the three gentlemen who got the prize in physics for groundbreaking contributions to our understanding of complex systems. You see that these three works of large body of work by three Nobel laureates are quite different, but the only connecting part among them is complex systems. Okay, so Professor Debashish Chaudhary gave a talk in November, I think 30th, on Parisi's work. So this work has been covered on spin glasses and things like that. So I will cover Manabe and Hasselmann's work today on Earth's climate, quantifying variability and reliably predicting global warming. Now, I must apologize in the beginning itself that their work is reasonably technical. Of course, they won't get Nobel Prize for trivial work. But in this talk, I am kind of making it trivial for general audience. The topics are quite complicated, like climate modeling is not easy. So I have somewhat made it really dilute. Okay, so for experts, apologies from beginning itself. Now, so I will basically go one by one. Manabe's work first, then I will go to Hasselmann's work in the second part. Now, he is part of GFDL, Geophysical Fluid Dynamics Lab in Princeton. So he came in Princeton. Well, he didn't come to Princeton first. He came to Weather Modeling Group in 1958. I'm going to just talk about GFDL a bit, and I proceed further. After his PhD, he just came to US, and he joined US Weather Service. That was the name of this lab first in Washington, DC. That lab came to Princeton after several years, and he worked under Joseph Smogorowski, who is a big name in fluid dynamics. And in fact, he was the founder of GFDL, Smogorowski. Okay. Now, this quote of Manabe is quite interesting. So after graduating with a degree in physics over 30 years ago, I chose a career in atmospheric science over particle physics. I was always worried about how my applied physics was viewed by mainstream physics colleagues. With the Nobel Prize in Physics under our discipline's belt, it gives me and climate modeling colleagues the credibility and recognition that we have earned for. Climate science is a real science. Okay, so Manabe's talks are, I mean, he seems to be very gentlemanly and very humble. That's what it appears from his talk. Anyway, this is his one of his comments I've quoted here. So this is about GFDL. So you have to go from the bottom. So this GFDL, 1955, is a weather bureau. So it started as a weather bureau first in Washington, DC. Then Manabe was in 1967, he came, and his first paper appears here, where he showed that CO2 will warm up the weather. Okay, that's what I'm going to discuss a bit about that. And then GFDL moved to Princeton. Then first climate model, where Manabe is a key player, appeared in 1969. Again, we go from the bottom. 75, greenhouse effect became part of climate model. 1980, supercomputer is built and housed in GFDL. Then 1988, IPCC is formed, which is a very important body for climate change. Then molecular ocean model is created in 1990. After that, 1991, IPCC report, a forecast model, then flexible. So you can see that GFDL is a leader in this field, and Manabe played a key role. Manabe appears in several of these reports. IPCC report, Manabe is the author of the first report. So he appears, I mean, he is a key member of this lab from 1967 up to 2007. And this page is created before his Nobel Prize. Please remember that. So it's not that his name came now, but this is a website before his Nobel announcement. Now, the paper he wrote in 1967 is considered to be the most influential climate science paper of all time. So it is titled Thermal Equilibrium of Atmosphere with a Given Distribution of Relative Humidity. Now, it's a very technical paper, though contents is quite, I mean, it's technical means it's not extremely difficult to read, but I'm just going to give a gist of it. Now, the second paper he wrote several years down the line in 69 is a model. So how to connect like ocean, in atmosphere, ice. So right now in climate as well as the weather, we need to take into account ocean, ice, and various factors like desert. All these are taken into account. And he is a creator of those models. I mean, and in Princeton, I think the first computer when it was built, it was in GFDL, and they were putting these models right away in these computers. Now, preliminary, just to get an overview of global warming, we need to just think of several ideas before that, simple ideas, but it's school physics, but let me just brush up. So this is the black body radiation spectra. So x-axis is wavelength and y-axis is intensity. So at a given temperature, visible range. So this is from the sun. So sun is around 6,000 degree Kelvin, and it is radiating in this band. So the peak is in yellow, right? Peak is in yellow. So what we get is the white light with the peak in yellow. Now the Earth, which is around 300 degree Kelvin, okay, is less than 300 Kelvin, but just 27 degrees is a good number to see. And radiation of that thing will be far in the right. Far in the left, small wavelength. Okay, so this is what you will get, large wavelength, large wavelength, far in the right, you'll go in that direction. 300 will be far, very far in the right. Okay, so it is in infrared, heat radiation. And you remember the lambda max T is some number. So this is the thing, lambda max T equal to that stuff. So given a black body temperature, it radiates with certain wavelength. So sun radiates in visible range, but Earth radiates in infrared range. Okay. Now atmosphere, glass, plastic, they are transparent to visible. I mean, visible can pass through this material or atmosphere, but it blocks infrared. Okay, so let's see an example. So you might have seen this structure. In fact, in mountains, they have this structure. So plastic walls or glass walls, and inside temperature is warmer. And here you can grow vegetables. Okay, so this is greenhouse structure. In fact, the car, when it is parked in summer, inside is terribly hot because the sun can get inside. You see the sunlight is coming inside. But so this glass is transparent for visible light, but the surface of the car as well as this plants and so on inside the thing, they radiate in infrared, and glass will block the infrared to go through. So infrared, what is generated inside is not going out. So inside gets warmer. And the same thing happens of a car, especially in summer. I mean, it just becomes very hot. So we have this structures in shopping malls. Okay. Now, this is a not good design for Indian climate. The sun comes in and it just warms the air inside. Okay. So it's just infrared which is warming it. We have a building inside. I mean, you can guess which building is this one. This is also a greenhouse building. Okay. So let's look at the atmosphere. These are glass, okay, glass or plastic. Now let's look at atmosphere. So we have air, of course, with oxygen, nitrogen maximally, but we also have CO2, moisture, H2O, methane, other gases as well. Okay, Now, these gases, H2O, CO2, methane, nitrous oxide, and ozone, so sunlight is coming from the sun. Earth surface absorbs it. It radiates in infrared. CO2 in the atmosphere will absorb it, but it re-radiates, okay, again in infrared zone, and that comes down. So ideally, if there was no atmosphere, then all the light coming in would be radiated back in infrared, and there will be equilibrium. But because of this air, CO2, water, and methane, it goes out, but it comes back. Okay, so this keeps the Earth warmer than what it would have been. That is the whole idea. Earth is warmer. In fact, it's good for us that it is warmer. So I'm going to show you the numbers. It's really easy to calculate. You can do it yourself. How these gases are contributing for warming of the Earth. But too much of warming will create problem, and that's the problem. That's the issue. If you have more CO2, then it will warm more than what it is today, and that is what was done by Manabe in his Nobel Prize winning work. So this is another slide of same thing. Here, one additional thing is this water condenses. So condensation releases latent heat, and that creates issues. So water is an important player, okay? And phase transition of water is also a big player, which I cannot discuss in today's talk, but water plays a big role, which I will going to state the result of Manabe in a while. So let's look at what is Manabe's work in a very simple words. So his Nobel speech, his talk is quite interesting, okay? So you can just go to Google, YouTube, and you can hear his talk. It's around 25 minutes. It's on YouTube. And I just took from his talk some material. Well, most of the material in next few slides are from Manabe's Nobel talk. So this is Earth. Now, sun is coming, sunlight light is coming on the Earth's surface, and the average energy incident on Earth is 240 watt per meter squared. Okay, this average. So there is a dark side, or the night side has no light coming in. So if you average out over the whole region, it's 240 watt per meter squared. Now we can use Stephen's law. So sigma T4 is 240 watt. That gives us temperature of the Earth is 255 Kelvin. Now this I did it. So this number is correct. And that comes out to be minus 18 Celsius. So if there is no air on the Earth's surface, the temperature of the Earth would be minus 18 degrees, where I won't like to live in that atmosphere, that Earth. Fortunately, Earth temperature, if you look at the surface temperature average right now, is around 288 Kelvin average. Okay, I mean, there's some places which are cold, some places which are hot. If you average out, is 15 Celsius. So the difference is 33 degrees, and the difference is because of greenhouse effect. Okay. This is known before Manabe. Well, of course, these calculations are done in a lot of care, and Manabe contributed to this. But his contribution is what happens when CO2 increases in the atmosphere. So let's look at his work in slightly more detail. Okay? That is part of 67 paper of his. So Earth atmosphere temperature drops with height. Okay, now when you're flying in the aeroplane, 8 kilometers above, the temperature is minus 50 degrees or so. So this has been calculated. In fact, this calculation is not very difficult. 6.5 degrees drop every kilometer. That's what happens. That's because of adiabatic cooling. So temperature, so x-axis is temperature and y-axis is height. So the temperature is decreasing along this blue line. So right now at the height equal to 0, which is the surface, is 288 K. Okay. Now if you go down, go up. Go up. At some point it becomes 255 K, and equilibrium point. Okay, and you can think of this as a point where radiation is going up, and there's a balance. The sun radiation is coming down from the top, and here this long wave radiation, this is infrared, is going up, and there's a balance. So this would be the case for present constitution of the Earth gases. Now, this difference is the greenhouse effect. So if there was no gas, then it would have been 255 at the surface. But now, because of some gases, these gases, we have this difference is 33K. Okay. Now, so how, I mean, this is basically what is happening here is radiation is, Earth is radiating out, but these gases radiate back. And that radiating back is causing the heating. Now, what is the effect of increase of CO2? When there is more CO2, what happens? Now, this is, I mean, it's a detailed calculation, but the key point is that CO2, well, there's several key points. One key point is that CO2 makes the Earth, if you increase it, it becomes more opaque. Means transmission is decreased. Now, transmission decreased, that means so this point, earlier it was here, B point, which is point from which radiation, effective point. Okay, these are effective points from which there's a radiation, backward radiation. This backward radiation is coming. But if CO2 is increased, then this point will go down. And as an effect, so go down means the down point is higher temperature. So that means the effective temperature of the Earth will increase. So this is what happens, downward motion, because of one factor among many factors is CO2 is more opaque. More CO2 means more opacity of the atmosphere. Now, this point, which was 255 Kelvin, this point goes up. It's more opacity, so this point moves upward. And as a result, the upper atmosphere temperature is lower. So there are two, this supposedly people did not believe him. This was controversial. More CO2 is put in the atmosphere. The upper part of the atmosphere, which is called troposphere, will be cooler and the bottom part will be hotter. It's not that everywhere in the Earth temperature increases. The upper part is cooler and the lower part is hotter. Now here, another point which makes a key role is water. Okay, so what, in fact, though CO2 is doing the opacity effect, water is also a major greenhouse effect. In fact, water content is more than CO2, and that because of also phase transitions, that creates that has a major effect. And I'm just going to show you the numbers. The detailed calculation I cannot present it here. So this is his calculation in his 1967 paper. So this is 150 ppm parts per million. So the blue curve is a 150 ppm. Okay, the CO2 content. Now, y-axis you can think of as height. Okay, so this is in terms of pressure, but it's basically you can convert it to height. So at the bottom we have this temperature somewhere here. Okay, supposed to be that number 17 Celsius. Okay, now here 285. Now, if I increase this, and upper part is here, the temperature is here. Okay, now when I increase this CO2 content to 300, then at the bottom you can see that the black curve is shifted to the right. It's getting warmer. So from blue curve somewhere here to black curve here. So it is shifting here, and that is around 2 degrees. Okay, that is what his calculation in 67. He showed that if I double the CO2 content, then the Earth's surface temperature will rise by 2 degrees. 2.3 degrees is what he said. And so this is by doubling the CO2 content. And here you see that at the top, temperature has decreased. This is going to the left, temperature has decreased. So x-axis is temperature, please remember. So going left means decrease, going right means increase. Now, if I increase it from 300 to 600, then there's a further decrease at the top, but further increase, further decrease in the top, but increase in the bottom. At the surface temperature increases further. So each time I double the CO2 content, there is a doubling of temperature at the surface and reduction by factor 2 at the top. Okay, so the next slide is precisely this. So here H2O feedback. So he has put in water feedback, and that is 150 ppm to 300 ppm. This is a CO2 content. So the temperature rise is 2.3 degrees Celsius. And if I go from 300 to 600, so there's a double, then another double. So another increase of 2.3 degrees at the surface. Now, without H2O feedback, it is 1.3 degrees. Okay. So it turns out CO2 and H2O are major factors. Now, supposedly sulfur dioxide. Okay, now I'm not an expert of this. I have not done these calculations. SO2 is helping us in elevating this increase. So because of sulfur dioxide, sun's rays are shielded and we get less increase in the temperature. Now, some of us, like, I mean, we are going through a pretty bad winter phase. Now, it's not that H2O sitting up there is going to increase the temperature of the surface. So it's a major complex problem where there's a condensation, there's a blocking of the sunlight. So it's not simply that there's more cloud, then the surface temperature is higher. Sometimes cloud helps, but if the sunlight is not going to come inside the surface effectively, then surface is not getting heated up. So it's a complex calculation. I think it would be interesting calculation to see why is our present, like last 2 weeks has been so cold. Now this is because of this H2O. H2O plays a big role. It is clear from right now, we can just see that how the Kanpur weather is behaving. Now this is a 69 paper of Manabe, where these are the factors. He kind of sketched those times. Computers were just coming up. I mean, they were very, very slow those days. And what are the factors which are to be taken into account in making model? Land, ocean, there's a coupling between ocean and ocean and land, so these are stuff, and equation of motion, thermodynamics, a water vapor equation. So he made this picture, and all these things are coded inside a computer. Of course, number of variables we keep in the code is a number of grid points. I'm going to show another slide where I will just show you how the weather modeling or climate modeling is done. If you increase the number of points, it will be more accurate. If you decrease it, it will be less accurate. Okay, and we'll differentiate weather and climate in a while. Okay, so let me just come to that. That becomes more apparent in Hasselmann's work. Here also, climate like 2.5 degree or 2.3 degrees or 2 degree change is not every year. In fact, sometimes the weather yearly temperature may decrease for a while. So these are long-term effects, and that's where Hasselmann's paper, which I'm going to show you in the next half of the talk, where we'll see how climate is getting affected by local weather changes. Okay, so this is part 2. So part 1, I'm done. So this is a brief glimpse of what can CO2 do to our surface temperature. And indeed, I mean, till 1990s, people did not believe it. Even now, there are disbelievers of global warming. But presently, almost everybody believes that CO2 is increasing the surface temperature. Now, these calculations are supposedly quite robust, and robust is there are some error bars, and there are other factors which come into play, but these are reasonably robust. And there's a worry right now. I mean, I didn't show that plot that CO2 is really exponentially rising at present. So that's a real worry. And we really don't know. It could be irreversible damage to the Earth, and the temperature may be really going up hugely after a while. Now, part 2, this is work by Klaus Hasselmann. He is in Germany, Max Planck Institute of Meteorology, Hamburg, Germany. And he is for the physical modeling of Earth's climate, quantifying variability and reliably predicting global warming. So this is a prize motivation citation. Now, he is born in 1931, and he was affiliated with University of Hamburg. So you can go to Wikipedia and look at his bio. And in fact, he was in UK for a while. In his childhood, his schooling was in UK, and then he moved back because it was wartime. So he moved back to Germany after that, after the war. And he was the founder. He's the founder director of Max Planck Institute of Meteorology. So this is from Wikipedia, Hasselmann model of climate variability, where a system with long memory, the ocean integrates well, for example, the ocean, integrates stochastic forcing, thereby transforming a white noise signal into a red noise one. Okay, I'm going to come to that. White noise and red noise, I will describe that. I colored it green. Thus explaining without special assumption the ubiquitous red noise signal seen in the climate. Red noise means long time thing, okay? Low frequency, long time effect. Okay, so we'll try to cover some of it in the next part. So how is climate model or weather model? So these are schematic. So earlier models had these equations. So we have a equation for the velocity field of the air, U, V, W, 3 components. Temperature, theta is the temperature. Then mass of the air, humidity, Q, moisture content, and gas law, okay, ideal gas law. So this is a partial difference. These are partial differential equations. So we on the Earth atmosphere, also ocean. You need to put that. So right now, ocean is not included in this. That's why ice is not included. So this is pretty primitive model. Okay. Now just imagine that we put on the atmosphere. Now it's a 3D atmosphere. So we make a 3D grid. So this is longitude, latitudes, latitude like that, longitude, and height. Now it's a 3D mesh, and at every point there are these variables sitting there: U, V, W, theta, rho, Q, and now we solve it in a computer. Now, finer the mesh we make, better the prediction will be. Okay. Now that's why we need a pretty fast computers to make a weather forecast. Now, weather forecast is for 3 days, 5 days, 10 days. But climate modeling, of course, we can't make a coarse grid, but fine grid. We make a coarse grid. Means here we don't take large number of points in horizontal and vertical directions, and but we take a coarse grid and we simulate it for climate. So same set of equations are simulated. Is that we coarsen it in climate, and weather is for so climate will be your grid, the delta T, in jump will be maybe days, so that we can reach 100 years, 1,000 years, or even 10,000 years, or even longer. So people are trying to simulate back in history 1,000,000 years. Okay, so when were the ice ages in the past? So in fact, we have some data from digging out ice in Antarctica, ocean digging, and so on. We can figure out what was the Earth's climate years, in the past. So people are trying to go back, and that will validate our model. How good is our model? So this is the set of equations, and in fact, people like von Neumann, in fact, he was very optimistic that we can solve these equations and we can really predict weather very accurately. In fact, there's a quote that we can plan our vacation. When the weather is good, we can plan our vacation by von Neumann. So the idea is that these are essentially Newton's laws. So given the equation, given the force and mass, mass will be density, a force will be the right-hand side. Given initial condition, we can determine the future. Okay, Newton's law, it works. But it turns out it works, no doubt, but it has some other complications. Okay, so what are the issues? Of course, we need the initial condition precisely. So that requires huge number of grid points. And if you don't have good enough computers, we can't predict well. And second thing is this: some of these equations are inherently chaotic. They show chaos. So sensitive to initial condition. Okay, so I'm going to explain in somewhat heuristic ways what is chaos in the next couple of slides. So they show pretty nonlinear behavior, chaotic behavior. Okay, so that's what I'm going to show. So we digress to chaos theory. Now, this is prediction by Newton. Okay, so it was first discovered by Kepler that the planetary orbits are elliptical. Okay, here given the initial condition. Okay, now assuming a sun and a planet only. Okay, if you just think of two bodies, then it can be solved exactly. We do it in our mechanics course. So this we can compute it. This is a trivial derivation now. So given the initial condition, I can exactly figure out where the planet is. Okay. There's no problem. This is done. But if you just put three bodies, so instead of just keeping Earth, Sun, you can put Moon there, or think of three planets interacting with each other, and let's see what happens. So this was, in fact, thought, well, slightly around 150 years after Newton by Poincaré. And Poincaré thought of three-body problem. In fact, it was question posed during those days only, three-body problem, what happens? And people thought, oh, okay, it's trivial, it can be done. In fact, Newton himself tried to solve Sun, Earth, and Moon problem, but he could not solve it. There was a perturbative approach, but that wasn't a satisfactory solution. So I'm going to show a video of by Poincaré. So let's see, it should work. Oops. So you'll see 3 points, 3 bodies. They're equal masses, and you see how complicated motion that is. There's no analytical solution for this these trajectories, and this is chaotic motion. And Poincaré had a glimpse of it in his work. So this is called chaotic motion. I mean, we cannot write analytically what the motion of these particles are. We can do computer simulations, and we can do that. But some more complicated thing happens, which I'm going to show you by another example. So that's called sensitive initial condition. If initial condition of one of the particles is shifted slightly, okay, by shifted slightly, then what happens to the future of that particle? It turns out if I do 2 runs with slightly shifted initial condition, they will show very different final state. Okay, that's called sensitive initial condition. And I'm just going to show you by another example, which is connected with weather forecast. So this is paper by Lorentz. So Poincaré is Poincaré's paper is, I think, 1890, I believe, somewhere around that time. Lorentz paper comes in 1963. So this is 1963 paper. Please note the paper by Hasselmann is in Thales. Paper by Manabe is in Journal of Atmospheric Science. So they are not nature papers or none of those. So they are technical papers and in the typical journal. So that's a comment I want to make. So this is paper in atmospheric science. It was kind of not taken notice of till chaos became popular in 1970s. So around 15 years later, it was it got noticed. So I will not read this abstract. I will illustrate it what happens in Lorentz equation. So this is convection. Okay, so this is the Lorentz equation is for thermal convection. So we have hot plate below and cold plate above, and the fluid in between. Okay, so we know from school physics, the hot flow will go up. So it is going up here and coming down. Hot fluid is going up and coming down. So we have velocity field and there's a temperature. So Lorentz thought, let's model this field by 3 variables. It's an approximation, but we just take 3 Fourier components. This is a Fourier expansion. So I just take 3 components, 2 for temperature field, theta, theta 1, 1. So these are all Fourier modes. Kx and ky is 1, 1. Okay, so this is along x and along y, 1, 1, and 0, 2. So this is another variable. And velocity field is the 2 components in 2D. So u1, 1. So I need 3 variables, theta 1, 1, theta 0, 2, and u1, 1. And he derived the equations for that. Okay, it's pretty trivial. You can plug in those equations which I showed you. It's a 2D system, not 3D. So number of variables decrease. If you just be at it, you can solve it. So these are 3 equations which Lorentz wrote. So x and y are theta 1, 1 and u1, 1 respectively, and z is theta 0, 2. Okay, so these are nonlinear equations because you can see that right hand side involves product of 2 variables. Okay, so this is a nonlinear. In fact, there are several nonlinear terms in this equation. Now, these are, please remember, there are Fourier modes of this velocity field. So what does it mean? Let's interpret it. we can simulate it on a computer. In fact, Lorentz did that in 1963. This is, you see, roughly same time. Manabe in 67. Hasselmann is a bit later, 76. So in fact, he's before Manabe's work. So he put in a computer. Those computers were slow. And the story goes that Lorentz put initial condition and he solved these equations. And then he changed the initial condition a bit and he went for T. Okay. And he came back and he saw that the output was very different when he changed the initial condition a bit. And that is surprising. I mean, anybody who does numerical analysis, if you change the initial condition slightly, we expect the error to be not so significant, you know. And that is a big thing which he reported in his paper, which was didn't take notice of. People will still believe that if I change the initial condition a bit, big deal, it's not going to change much. But let's see. So for this parameter called Rayleigh number, okay, so this small r, 0.5, all the modes are zeros. That means there's no convection. So velocity is zero. It's conduction. There is heat transmission by conduction. But if I make this r to be 5, that is 5. So that means it is below, 5 times above the critical Rayleigh number. Then we start getting rolls. And it's a constant roll. So this is a theta 1 mode. So you'll get, this is not changing with time. X-axis is time. Please note that X-axis is time. And the rolls will just go on like that. No problem. It just go on like that. Now, when I go to R equal to 30, in fact, this was done by Lorentz. This is one of the parameters. Well, I exactly don't know, but one such parameter. And then he finds that this mode, theta 1 is changing sign. Positive, negative, positive, negative. What does it mean? So the roll is going that way, and then it turns around that way. So clockwise and anti-clockwise. That's what is the interpretation of this. Okay. So, and it's random. I mean, you can see that it's random. Okay. So this is what we get in this simulation. Still, I've not shown you what initial condition effects are, but I'll show you in the next slide. Okay. But let's see what are the different states of the system. And different states of the system are steady rolls, this is called steady rolls, and this is called chaotic rolls, where things are, this is called butterfly diagram, where, so we are 3D picture of these three variables, okay? And these are three variables, and you plot them, you go one with there. So basically it shows clockwise motion or anti-clockwise motion of the convection rolls. Now let's see this movie, this by Professor Math. So I start exactly the same butterfly diagram in chaotic regime. So we have all the three initial conditions sitting here, but slightly different. You can see that in the beginning, they will just follow the same trajectory. Okay, so let's play the movie. So they are all going together. Three initial conditions were very close to each other. Still together. That means my output is roughly same, but after some time they start deviating. The line is getting thicker. Now they start deviating significantly, and after a while they'll be very, very different. For example, one point will be in the right lobe, other point will be in the left lobe. You can see that they are very different. So that is what it means for whether if my measurements cannot be accurate. Huh? So if my measurement is off by the real value by even 1% or less than 1%, my prediction will be off by in 3-4 days. My prediction will start going haywire. Okay, that's the complexity. We are not able to. We cannot predict for a year forecast, weather forecast, and that's where Newton's idea that deterministic world is deterministic. You can predict future forever. That doesn't work. Okay, this is class. It doesn't work. So weather shows chaotic behavior. Now please keep in mind that these are the initial conditions of the Fourier modes. Okay, these are not. So I'm going to make a comment in 1 minute. So these are Fourier modes amplitude change. So you are changing the big scale mode by simultaneously. It doesn't mean that there's a butterfly who is flipping here. Okay, so these are change in the amplitude of the Fourier mode. So makes prediction harder. It's true that it makes prediction harder, but it is not as bad as butterfly effect. Okay, in the sense changing the real space coordinate by real space variable by some small amount is not same as changing a Fourier amplitude by a small amount. That's different. And there's a nice quote by Mecom, he's a turbulence theorist. In reality, the butterfly can flap its wings as much as it likes, but it is not going to cause a stop. Okay, so I think if you think about it, it's quite obvious that this is, so-called a PR thing. Butterfly effect is not really there because winter comes every year in winter time. December, January are cold. It's not changing with all the changes. So there is certain robustness in the weather and climate. Okay, but there are changes. Of course, there are changes. We cannot predict what happens 10 days down the line because of chaotic nature. Okay, so both are there, but one can't simply imply, oh, nothing is predictable. That is what Hasselmann is trying to show that in his work. So this is another slide. This is our work, group's work. Instead of 3 modes, we can keep more modes. Let's say 7 modes. I will not tell you which modes, but then things are not as bad. At 30, a system is reasonably well behaved. In fact, things are not chaotic till 40. So Lorentz equation shows chaos around 24, but with more modes, we get chaos much later. What happens if I keep 1 billion modes? The question is, will the chaos come or not? So it's a mixture. So that's what I'm going to show you another movie a bit later. So when you have large number of modes, this chaotic nature at large scale is suppressed. At large scale, a small scale will show chaos. Now let's look at a brief thing on Hasselmann's work. So as I said, I diluted some of this their work because to just make it interesting and make it popular. So these are the 2 papers for which he got, which is cited. There's some more work. Nobel Committee normally gives a citation, but these are papers which are fundamental papers that made a impact in these fields. 1976 in Thales, stochastic models part 1 theory, and part 2 is 77. Okay, Hasselmann is a single author here, and he is a part of a group, the 2 authors. Now, so this is I'm just going to quote from his paper, part 1 paper, and let's just read it. I'm just going to quantify it, make it more dilute in the next slide. So this straight from his paper, the variability of climate is attributed to internal random forcing by the short time scales, weather. So climate and weather. So weather is short time and climate is long time of the system. Slowly responding components of the system, such as ice sheet, ocean, and variation in the Earth's surface, act as integrator of this random input much the same way. Heavy particles embedded in an ensemble of much lighter particles integrate the forces exerted on them by light particles. So light particles are like weather, and heavy particles are like climate. So let light particles collide on it. Heavy particle doesn't move much. This elephant doesn't move much. But if you wait for long enough time, there will be some movement. And that's how the climate change happens. Okay, so this is his work there. Now, one more point. So that is one part of his in that 76 paper. Thus, this is another part. Now, let me read part of it. So variability, climate variability is not to discover the positive feedback which enhances the small variation of external input or produce instabilities, but rather to identify the negative feedback. So this is important one. Negative feedback process which must be present to balance the continual generation of climate fluctuation by the random driving forces. Okay, so positive feedback. You can imagine that this weather will create acceleration of the climate change, but there is a negative feedback as well that will balance the growth and suppresses exponential growth suppresses the growth of the climate variations. Now, these are the equations I took from 76 paper. So we can think of set of variables, xi's and yi's. So xi is weather variables. Okay, they are short time scale variables. Right hand side is thing causing the changes in weather, and yi is the climate. Okay, and this is the right hand side of climate variable. Now you can see that the time scale of weather is much less than the time scale of climate. So tau x is the time scale for xi's, and tau y is the time scale of yi. So it's clear, no? Climate changes over centuries, and weather changes over, in fact, days. Or not even days, every hour. I mean, the things are changing every half an hour, the temperature is changing. So this is the scale. Now, this delta yi's, now things are changing slowly, so he makes a model. This is a kind of answered. This is an analytical paper. I mean, this is a theory paper. So he's making some kind of schematic picture of the weather and climate. So the weather is short time scale. So this is the time and covariance. So this is the weather, and climate is going like that. Okay, without negative feedback. This without negative feedback. This is growing linearly in time. This correlation. In Fourier spectrum of this, the small time scale will correspond to high frequency. Frequency is inverse of time. So this is weather frequency, weather effects, weather is at a high frequency. Now it has effect on the climate. And since it's linear in time, you can do Fourier transform. It's going to be 1 over omega squared. Okay, these are pretty trivial stuff. I mean, you can just do this analytically. So response is 1 over omega squared. Now, for small omega, this is response is huge. Okay, that's why you want to temper this growth. And then he says, well, instead of the linear growth, we make some negative feedback. So the same picture, but only changes is negative feedback. This one. So instead of growing all the way linearly, you taper it off, and that is going to not get g omega going to is 1 over omega squared, but there is a omega squared plus lambda squared. So there is a finiteness of the response. Okay, so this is the negative feedback, or he called red frequency. No, I mean the infrared frequency. Infrared means low frequency, and colored or white noise is high frequency. Okay, so this is the part. So the two parts. One is high frequency of high frequency effects of the weather impacting the climate, and also the negative feedback balance. I mean, makes the explosion controlled for the climate. So that is his fundamental work of Hasselmann. Now, I thought, I mean, this is probably not the best way to explain it, but I thought this movie will be kind of nice. So this movie was created by Mani Chandra of our lab. So this is a convection again, same 2D system. Now this is in a turbulent regime. Now there will be some part which is varying slowly, but you can see that there are a lot of fluctuations at different parts. Okay, so a lot of fluctuations at different local regions will be like weather, and long-term things going around will be climate. Okay, so this is a crude analogy I'm trying to make. So you can see, by the way, there will be some change, long-term change after a while. So things are going like that. Okay, you see that there is a thing going around. So these are velocity field is, well, doesn't mean the velocity is not, there's a velocity field going around, but there are some changes here. So there are some changes, and at some point there's a boom change. In fact, similar model, well, these are similar things are used for modeling ice cycles, or there are changes, no, when from ice age to not ice cycle, ice age to warm period. So there are nonlinear effects which kicks off after a long time. Okay, so these are called variation. I mean reversals of the systems. It happens for the magnetic field of the Earth as well, which happens on long time periods. But there are turbulence embedded in it. So turbulence can be thought of as a high frequency, and climate can be thought of as a long time scales. Now Hasselmann has further work on fingerprinting of climate change. Now this I will not get into. In fact, I don't understand it very well. So from given the signal, how do I know that there's a climate change? And so we can collect data from the oceans or ocean waves. And from that, you can figure out there's a climate change or not. These are fingerprints for climate change. So I'll just summarize now that global warming is real. And now Manabe's work, in fact, with it, people believed in global warming for at least last decade or so, for sure. Yeah, there were doubters, but now they are not there anymore. And he made a fundamental calculation. And in fact, that 67 calculation is indeed that he showed that the doubling of CO2 will increase the temperature by 2 degrees. Okay? And this was pretty it's an idealized calculation, but it holds. I mean, even with full DNS, it holds. A small time scale is weather and long time scale is climate. And Hasselmann's work, as well as Manabe's work, I mean, his models, they connect climate and weather. And we are able to make definitive predictions for the Earth climate and weather as well. Of course, there are many questions which we know we're not certain how much global warming will heat up the Earth. There's still a doubt in long run. I mean, of course, the CO2 content itself is not certain how far it will go. So these are topics which are still being debated. How much ocean is going to rise over next century? It's not. I mean, there are predictions, but there are debates whether number is correct or not correct. Okay, so I think I'll stop here, and I'll be happy to take questions, which I'll try to answer as best as I can. Okay, Shiva, I can stop now.
Thank you so much, Mahendra, for this excellent talk and for making it quite instructive for the students, giving the content of the work. And the floor is open for questions. Yes, I think, Professor Madhav Ranganathan, please open your mic and go ahead.
Yeah, thanks, Mahendra, for the wonderful talk. So, I mean, regarding the people who doubt climate change, okay, there is one very prominent physicist, Freeman Dyson, who was a skeptic. So, yes. And he kept saying that the models of climate change have overestimated the effect of CO2 and not taken into account the beneficial effects of CO2, such as increased agriculture inputs and a lot of other things. So do you have an idea of what it was that he was criticizing and why he was so against this?
So no, I'm sorry, Freeman Dyson, I don't know exactly what his criticism was, but so you can look at Manabe's video. I've been seeing it in recent times. So he makes several things which are kind of, now we can see it. He says, for example, that moisture content will increase in the atmosphere, so there will be more rains in coming up. Okay. Now he says, but more rains doesn't mean it's beneficial. So more rains in the regions where there are already rains, and less rain in regions where there are less rain. So that creates a water differential. In fact, I saw a video. So you can say that more rain will be good for agriculture, but it can also cause flooding. So I think Freeman Dyson, possibly I should not say in public, but I think these are detailed calculations now, which done by atmospheric scientists, which definitely say that there's global warming effect, and we can see it. By the global warming also has predictions that there'll be changes. So there'll be cold period. I mean, we do get cold periods more than what we get before. Also, the changes will be very abrupt. The cyclones are more intense now than before. So all these things are predicted and they come true. So I think Freeman Dyson's, I believe, well, I'm not an expert, I must say. So I think one can ignore his objections to that at the moment. That's my layman's thing from whatever I know.
Okay, thank you.
So there is another raised hand in the audience, Pankaj.
Yeah, so it was a very nice talk. I was just wondering about the model that you showed, that two-mode model by Hasselmann. So in that, what were those variables? Those variables were temperature, or it was something else?
No, it's not a two-mode, Pankaj. It's a schematic paper where xi is supposed to be generic. Xi is xi. I mean, this is a vector. It's not two variables. Xi is set of variables which are climate variables. So we can take a large number of Fourier modes, and you can take the high frequency Fourier modes as call them weather, and low frequency mode is climate. That's something which you do, and one can think of that way. So it's not a two variable. It is many variables, but you're truncating this scale separation. We use it, no? So high frequency modes are one set of variables, and low frequency modes are another set of variables, and you make a demarcation.
But in that case, we have the intermediate modes also, which will have the different time scale, and that will affect the motion due to turbulent motion.
So he did not. I mean, that paper is not discussing the. He has a clear separation of variables in that, which is used by people. The multi-time scale papers are there, or even books. So his paper is it's an analytical paper. It's stat make non-equilibrium kind of paper. He has no mention of. I mean, the second paper discusses with ocean effects of weather on ocean temperatures. Okay. So second paper is more connection with the atmosphere, which I didn't cover. But first paper is more of a idea paper.
Okay. Thank you. Thank you.
Okay. Thank you, Pankaj. And any other questions?
So there is one chat box. Something is there. I don't know which.
So this none.
No problem.
Any other questions?
Hello, sir.
Yes.
Yeah, so I have some basic doubt. So you showed that the grid for the Earth's surface, we do the CFD modeling. So what kind of boundary conditions we used for weather prediction as well as climate prediction?
Okay, so boundary conditions for along longitude and latitude is not periodic. Basically, we are all it covers is periodic. Well, kind of periodic, no? Theta and phi.
Yeah.
In the vertical direction, there is a troposphere. So you go all the way up to 50 kilometers or so, and you put the upper surface temperatures, upper surface variables at the top. So we basically go in the vertical direction, and we do that. But of course, these are coarse grids. So coarse grids are typically presently 3 kilometer by 3 kilometer along horizontal directions. In vertical direction, there will be something like 100 layers in the vertical direction, which is covering around 50 kilometers. Okay, so it is pretty coarse grid, but at the small scale, I mean, this is the time scale and length scale of the system. It's reasonable. People, of course, want 1 kilometer grid. That's a desire for weather forecast, and they are moving towards that. So that's the boundary condition is realistic for the surface, bottom surface. Is people take the terrain into account, mountains, the ocean. So these are all finite volume codes where people are taking care of things quite well. And weather forecast is quite accurate. I mean, well, in India, we are not so lucky, but in the West, they make a forecast quite accurately. I mean, they say 4 o'clock, there will be a rain with that much probability, and 4 to 4:30, there will be a rain. So it's quite accurate now.
Like we use the initial temperatures over the surface of the Earth and flux on the outer atmosphere, flux coming inside the atmosphere.
Yeah, yes. So that there are feedback coming. The right hand side is a forcing. Yes. So all that
because
is
that flux is more. That flux affects more the system rather than the initial temperature at the surface.
All of it matters. I mean, here, all of it matters. Not only the sun's feedback, there is a movement from the ocean, for example, monsoon. Things are moving in from the Kerala coast into the land. All that matters. So everything matters in this. Okay. So large scale, well, I mean, there where scale separation makes the difference, but large scale mode will matter more than small scale modes. But there is a impact of everything, and that's why we need high resolution simulations. Also, good modeling. So viscosity in these codes are not the kinematic viscosity of water or air. They are model viscosity. These are parameterization. Because at that grid, if you are aware of large eddy simulations, we have viscosity is not same as ordinary viscosity of water. So these are put in as parameters in the code. And accurate modeling is useful for these stuff. I hope I make myself.
Can you ignore the smaller scale things for the climate prediction?
Yes, for climate predictions, people ignore it and they do careful modeling. Yes, for climate thing, it is time step is bigger and space step is also bigger because they have to go to 100 years. It's true. So that's the difference between climate.
One more question that. This chaos theory and instability theories are completely two different things, right?
So instability is at the onset. Instability is more or less understood. Okay.
Yeah.
But chaos theory is when you are away, far away from the instability regime, then all these nonlinear effects come in. So the Rayleigh-Bernard convention, which I showed you, instability is very easy. I mean, this is supercritical pitch 4 bifurcation. But problem is when you have large parameter, when heating is more, then what happens? And that's where the problem is. So chaos is more complicated than instabilities.
So when we say this butterfly effect, so it is actually the perturbation by the wing flapping, and
so it's as I said, it's amplified thing. It's for press. Yeah. It is not really true. So initial condition sensitivity is there in the systems, and I showed you in the movie that if you change the initial condition, it shows up in the final output. Okay. So that's why we can't forecast accurately for long terms. So, but butterfly is true. I mean, that if something happens at a very small, butterflies flipping in Atlantic Ocean doesn't mean India's weather is affected hugely. Okay, that is a dramatization, which is not true.
Okay,
thank you, sir.
So thank you, Kavan. And there is another raised hand, Priya Deshwal.
Hello. Yes, sir.
Yeah, please go ahead.
So thank you very much for this interesting talk. I just want to ask that the main difference between chaos and turbulence.
Okay, so there are large number of differences. So just to give you few, chaos theories typically is few degrees of freedom. Few means could be, well, Lorentz equation is only 3. 7-mode model, which I described, has 7. So something like 20 modes. Beyond that, we don't study in chaos. 20 variables, okay? In turbulence, we have huge number of variables. I mean, it could be millions or billions. Now, there are large differences. For example, the 2 particles in a chaotic system will diverge exponentially. This is called sensitivity initial. Their divergence is exponential in time. But in turbulent flows, if you take 2 particles and see the time evolution, it's a power law. In Taylor diffusion, which is the good model for diffusion, is a T to the 3/2. So the distance between 2 particles in turbulent fluid will be T to the 3/2. So there are differences because the degrees of freedom in turbulence is much more. Turbulence also, you see there are a lot of scales, large scale, small scale. So the picture I showed you, this vortex going around in real simulation, that's a turbulent flow. We had pretty much going around. I mean, things are stable as well. The large scale modes are stable. In fact, that is somewhat connected with Hasselmann's work. So turbulence will be chaos, but overall, the stability is given by large degrees of freedom. That makes the system somewhat stable. Okay. Now, these are kind of hand-waving arguments, but we can say these things for approximately accurately. Well, these are contradiction terms, but this is what we understand from simulations and experiments. Things are not so unpredictable as chaos theory because we put in large degrees of freedom. Okay. Weather is climate. I mean, look, winter will come next 12 months later, no? And if it had to be chaotic, then you would know, you would expect that things will be just go haywire. That's not so because we have large degrees of freedom. And that's why there is a certain periodicity in the system, a certain order in the system. Okay, I hope I answered this question in a short while.
Yes, sir. Thank you, sir.
Thank you.
Thank you. Any other questions? Okay. So if there are no other questions, let's thank Professor Verma for this excellent talk and for clarifying all the questions kindly. And thank you all for attending. Thank you.
Okay, thanks, Shiva, and thanks everyone for attending. Okay, so will leave. Thank you.
Okay, so see you all.
See you.